Hello everyone, in this lecture I will discuss complex numbers. Now let's start by defining what is a complex number. A complex number is formed out of two real numbers. So if we have a and b as two real numbers, the complex number z is defined as a plus I b. And in this case here, I stands for imaginary and I equal to square root of -1. Sometimes z can be written as a and b in such a way the real part of z equal to a and the imaginary part of z and it's equal to b. So z equal to a plus ib. This is the real part and this is the imaginary part. Note that a plus ib is not equal to b plus ia. Examples for complex numbers: z, let's name it 1, equal to 3 plus 2i. In this case here, the real part equal to 3 and the imaginary part equal to 2. Now z2 as another example equal to -5.3 plus 26.9 I, and again the real part it's equal to -5.3 and the imaginary part equal to 26.9. Again another example here, z3 equal to -48, for instance, 0.7 I. In this case here, the real part equal to 0 and the imaginary part equal to -48.7, and z4 equal to 100, for instance, and in this case here the real part equal to 100 and the imaginary part equal to 0. So from these examples we can state that the real part could be any number starting from 0, could be negative, could be positive. Same thing for imaginary part, it could be 0, positive or negative. Now rather than using a and b numbers, we use variables like x and y. So in this case here, z equal to x plus I y, and this is called complex variable. In such a way, x is the real part of z and y is the imaginary part of z. So far we defined a complex number a plus ib. We defined also a complex variable z equal to x plus I y. This is complex number. In such a way, a and b, it could be any numbers, and this one here is complex variable. Again, x plus iy does not equal to y plus I x. If x is not equal to y. Let's have graphical representation of a complex number. Let's use rectangular form of a complex number. Assuming that this is the x and y coordinates, so this is x and this is y. Now z, it's equal to x plus I y, and z can be represented by a vector r in such a way, this is a vector r, which is z in this case, in such a way it has an intercept with the x-axis and intercept with the y-axis. So if this is theta here, this point here is x and y. Now, the polar form of a complex number, the intercept with this one here with the x-axis, so x in this case equal to r cosine theta, and y in this case here equal to r sine theta. Therefore, z equal to r cosine theta plus I sine theta. If we use the Maclaurin series, so e to x here equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on. Therefore, this series can be end up with x to the power n over n factorial from n equal to 0 to infinity. So this is e to x. Again, by using the definition of sine x equal to x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial minus x to the power 7 over 7 factorial plus and so on. And we also use the expansion for cosine x equal to 1 minus x squared over 2 factorial plus x to the power 4 factorial minus x to the power 6 factorial plus and so on. From the definition of sine and cosine and the definition of e to x, we can see that e to I x equal to 1 plus I x plus I x squared over 2 factorial plus I x cubed 3 factorial plus and so on. So we just substituted, rather than using x here, we used I x. Remember that I, it's equal to square root of minus 1. Therefore, I square equal to minus 1. I cube equal to minus I to the power 4 equal to plus 1. I to the power 5, it's equal to I to the power 6, it's equal to minus 1, etc. Therefore, if we back to this one here, we can rewrite e to ix in this one here equal to 1 minus x squared over 2 factorial plus x to the power 4 over 4 factorial minus x to the power 6 factorial, etc. plus I times x minus x cubed divided by 3 factorial plus x to the power 5 factorial minus x to the power 7 factorial, and so on. As we can see here, this part is cosine x and this part is sine x. Therefore, and this is very important, e to I x equal to cosine x plus I sine x. Therefore, z equal to x plus iy, and this is, remember, this is the Cartesian representation of the complex number, equal to r times cosine theta plus sine theta with I here, and we use here x equal to r cosine theta, y equal to r sine theta, and we just define that cosine theta plus I sine theta, it's equal to e to I theta. So in this case here, this will be equal to r e to I theta, and this is the polar form of z. R in this case is called modulus, or the magnitude of z. So r equal to magnitude of z, or r equal to modulus of z. Theta is called argument or phase of z. So theta can be represented as argument of z. Based on the above, the magnitude of z equal to r, which equal to square root of x square plus y square, and theta is argument of z, which equal to tan inverse y over x. We just used this figure in here to find the magnitude of r, which is r, this one here, and theta, tan theta, it's equal to y over x. Again, e to I theta, it's equal to cosine theta plus I sine theta, and from this one here, if theta equal to 2m pi, now if we substitute, this part is always equal to 0 because it's sine 2m pi m 0, 1, 2, 3, any number here, it's always 0, and cosine 2m pi, it's equal to 1. So from this definition here, e to I 2m pi is always equal to 1. Therefore, we can generalize e to I theta, it's equal to e to I theta plus 2m pi, because this part here it's equal to 1, and m here equal to 0 plus minus 1 plus minus 2 and so on. Remember, whenever you take m equals 0 and theta greater than minus pi less than pi, then the value of theta is called principal value. Let's define a complex conjugate. Whenever you replace I by minus I, in this case, this is called a complex conjugate. So for every I, you replace it by minus I, and you will get in this one here, complex conjugate. And assuming that if we have Z equal to X plus IY, the complex conjugate, placing star over Z equal to, now you replace I by minus I, so it's equal to X minus IY. So this is the complex conjugate of this one right here. And again, the argument of the complex conjugate of Z, it's equal to minus the argument of Z. Using the polar form of Z, so Z here equal to R e to I theta. Now the complex conjugate here equal to R e to, rather than using I, we should use minus I theta. The definition of complex conjugate is the mirror image of Z about the real axis in the complex plane. Like in this one here, this is the mirror image. So if this is Z, this will be Z star, or the complex conjugate of Z, assuming that this is X and this is Y. Now let's discuss how to add two complex numbers. If Z1, for instance, equal to X1 plus IY1, Z2 equal to X2 plus IY2. Now Z, which is equal to Z1 plus Z2, in this case here, you add real with real and imaginary with imaginary. You cannot add real with imaginary or imaginary with real. So Z in this case here equal to X1 plus X2 plus Y1 plus Y2, in such a way this part here is the imaginary part and this part here is the real part. It's very important to note that the magnitude of Z does not equal to the magnitude of Z1 alone plus the magnitude of Z2 alone. It's not correct. In subtraction, we actually follow the same procedure as addition. So if we would like to subtract Z1 minus Z2, in this case here, we subtract real from real and imaginary from imaginary. We never mix real with imaginary upon adding or subtraction. In this case, it's equal to X1 minus X2 plus Y1 minus Y2. This is the imaginary part and this is the real part. Let's have an example. If Z1 equal to 2I and Z2 equal to minus 0.5 minus 3I, calculate Z equal to Z1 plus Z2 and Z equal to Z1 minus Z2. Now let's do the addition here. Now z equal to z1 plus z2, this is z1, so the real part for z1 it's equal to 0, and the real part for z2 it's minus 0.5. So z in this case equal to minus 0.5 plus 0, just minus 0.5. Now the imaginary part for z1 it's 2, and the imaginary part for z2 it's minus 3. So when you add 2 plus minus 3, it's minus 1i. So it's minus I. Now for the second one, the subtraction, z equal to z1 minus z2, which equal to the real part for z1 0, the real part for z2 it's minus 5. 0 minus minus 5, it's 0.5. Now the imaginary part for z1 2, and the imaginary part for z2 it's minus 3. 2 minus minus 3, it's 5i. Now let's discuss multiplication. What's going to happen if we multiply two complex numbers? So if you have two complex numbers, z1 and z2, in this case, z here equal to z1 times z2, this is z1, z2, which equal to, now z1, it's x1 plus iy1 times x2 plus iy2. In multiplication, we just distribute this one on both real and imaginary, and this one on both real and imaginary. So in this case here, the multiplication will be equal to x1 x2 minus y1 y2 plus I x1 y2 plus x2 y1. Again, this is the real part of the resultant multiplication complex numbers, and this is the imaginary part. So the real part of z equal to x1 x2 minus y1 y2, and the imaginary part of z equal to x1 y2 plus x2 y1. What if we would like to multiply z with its complex conjugate? So let's have z times z complex conjugate. In this case here, x1 plus iy1 times x1 minus, because it's complex conjugate, iy1. You do this, you will find x squared plus y squared, or z squared, which is r squared, by the way, in polar coordinate. And therefore z equal to square root of x squared plus y squared, or square root of z times its complex conjugate. Example: calculate the product of the following three complex numbers. z1 equal to 2x1 plus iy1, z2 iy2, z3 x1 minus iy1. The simple way to multiply these three complex numbers is to multiply any two of them, then the result is multiplied by the third one. It's assuming that z, and name it I, is the multiplication of z1 z3, so in this case it's equal to 2x1 plus iy1 x1 minus iy1 and 2x1 square plus y1 square plus I x1 y1 minus 2x1 y1, or it's equal to 2x1 square plus y1 square plus I x1 y1. Now the final multiplication z, it's equal to zi multiplied by z2, which equal to, this is zi, 2x1 square plus y1 square minus I x1 y1 multiplied by I y2, this is z3, and the result equal to x1 y1 y2 plus I y2 to x1 square plus y1 square. Therefore, from this result here, z here equal to z1, z2, z3. From this one here, the real part is this one here, and the imaginary part is this one here. So the real z equal to x1, y1, y2, and the imaginary z equal to y2 to x1 square plus y1 square. Note, if we use the polar form for z equal to r e to I theta, we will see that the magnitude of the product of the two complex numbers is equal to the product of the magnitude of the complex numbers. Therefore, z1 times z2 equal to r1 e to I theta 1 times r2 e to I theta 2. In other words, it's equal to r1 r2 e to I theta 1 plus theta 2. Therefore, the magnitude for z1 times z2 equal to the magnitude of z1 times the magnitude for z2, which is equal to r1 r2. Unlike the addition, the magnitude for z1 plus z2 is not equal to the magnitude for z1 plus the magnitude for z2. In multiplication, the situation is quite different. Let's define division. Now, if we have z1 equal to x1 plus iy1 and z2 equal to x2 plus iy2, then z equal to z1 divided by z2, which equal to x1 plus I y1 divided by x2 plus I y2. Now, to perform this division here, we multiply the numerator and the denominator by the complex conjugate of the denominator. Now in this case here, if we multiply this one by the complex conjugate of the dominator, so it will be x2 minus iy2 divided by x2 minus iy2. In this case here, we will get, now since this is multiplication, you multiply the numerator by numerator, dominator by the dominator, you will get x1 x2 plus y1 y2 plus I y1 x2 minus x1 y2 divided by, when you multiply a complex number by its complex conjugate number, the result is x2 square, we just defined this before, plus y2 square. Now upon doing this, we can simply now find where is the real part and where is the imaginary part. In such a way, the real part of z is this one here, and the imaginary part is this one here. So the real part here equal to x1 x2 plus y1 y2 divided by x2 square plus y2 square, and the imaginary part equal to y1 x2 minus x1 y2 divided by x square 2 plus y square 2. We follow this procedure when the result of the division has to be in the rectangular form. But if we would like to perform this division in polar form, therefore z here, this one in polar form, equal to z1 over z2, which equal to r1 e to I theta 1 over r2 e to I theta 2, or r1 r2 e to I theta 1 minus theta 2. The magnitude for z equal to z1 divided by the magnitude for z2, and the argument for z equal to argument for z1 minus argument for z2. Let's have an example. Calculate the real and imaginary parts of this complex number z equal to 2 minus 3i divided by 3 minus 4i. It's not easy to find the real and imaginary part while z in this form. Therefore, if we multiply by the complex conjugate of the dominator equal to 2 minus 3i divided by 3 minus 4i multiplied by 3 plus 4i, 3 plus 4i. Therefore, in this case here, z equal to 6 plus 12 plus I 8 minus 9 divided by 9 plus 16. After all, it's equal to 18 over 25 minus I over 25. Remember, we multiply this with this, this with this, this with this, this with this. Now, in this case here, the real part of z equal to 18 over 25, and the imaginary part of z equal to minus 1 over 25. 5. Let's define de Moivre's formula. Back to the equation e to I theta equal to cosine theta plus I sine theta. Now, if we raise both sides to the power n, in this case, we will get e to I and theta equal to cosine theta plus I sine theta all to the power n. But e to I and theta is actually equal to cosine. Rather than using theta, we should use n theta. So replace theta by n theta here, plus I sine n theta. Simply, we can use this definition: cosine theta plus I sine theta to the power n is actually equal to cosine n theta plus I sine n theta, and this is actually called de Moivre formula. This formula is used very often in optics. It's very important, actually, formula in optics. Let's define power of a complex number. Z to the power n is equal to r e to I theta all to the power n, or r to the power n e to I n theta. And if z is so x equal to iy, then z to the power n, it's equal to x plus iy to the power n, or equal to r to the power n e to I n theta, which equal to r to the power n, and we should use here the Moivre formula times cosine n theta plus I sine n theta. Example: find 3 plus I square root of 3 to the power 6. To solve this one here, let's write it in polar form. So let's find r equal to square root of x square plus y square, which equal to 9 plus 3, or square root of 12. Theta, it's equal to tan inverse y over x, which equal to, in this case, pi over 6. Therefore, z here equal to 3 plus I square root of 3, which equal to square root of 12 e to I pi over 6. But z to the power 6 equal to 12 to the power 3 e to I pi over 6 times 6, which equal to 1728 here, cosine pi plus I sine pi, which equal to, this part here is 0, and this one here it's minus 1, so minus 1728. Therefore, the real part for z to the power 6 is minus 1728, and the imaginary part for z to the power 6 equal to 0. Example, find 1 plus I to the power 6. Again, let's find r equal to square root of x squared, which is 1, and y squared, which is 1 as well. So it's square root of 2, and theta, it's tan inverse 1 over 1, which is pi over 4. Therefore, z alone equal to square root of 2 e to I pi over 4, and z to the power 6 equal to 2 to the power 3 e to I 6 pi over 4, which equal to 8 cosine 3 pi over 2 plus I sine 3 pi over 2, or simply it's equal to minus 8i. Now in this case here, the real part for z to the power 6 equal to 0, and the imaginary part for z to the power 6, it's equal to minus 8. Now, the roots of a complex number is almost the same as the power of the complex numbers, with some modifications here. Now, as we defined z equal to r e to I theta plus 2m pi, and remember m equal to 0 plus minus 1 plus minus 2 and so on. Therefore, e to I theta equal to e to I theta plus 2m pi, and the nth root of z, which is z to the power 1 over n, equal to r 1 over n e to I theta over n plus 2m pi over n. So it's equal to r 1 over n times cosine theta over n plus 2m pi over n plus I sine theta over n plus 2m pi over n. Now, based on the n value, we can find the nth root for the complex number z. Let's define functions of a complex variable. If f of z is a function of a complex variable, it's equal to u x y plus I v x y. Therefore, the real part of this function complex variable is uxy, and the imaginary part is vxy. So the real part of f z here equal to uxy, and the imaginary part of fz equal to vxy. Example, put the function fz equal to z squared plus z in rectangular form. Now to solve this one here, fz equal to x plus iy squared plus x plus iy. Now in this one here, x squared minus y squared plus 2i xy plus x plus I y. Now add the real with the real and the imaginary with the imaginary. You will get x squared plus x minus y squared plus I 2x plus 1 y. Therefore, this is the real part and this is the imaginary part. And we just placed the function f of z in rectangular form. U xy equal to x squared plus x minus y squared, and v xy equal to 2x plus 1 y. Let's define the exponential and trigonometric functions. Now, if the exponential function of a real variable f of x equal to e to x, then the corresponding function of a complex variable z is f of z. In this case, it's equal to e to x plus I y, or equal to e to x cosine y plus I sine y. Therefore, the real part for this fz here, it's e to x cosine y, and the imaginary part is e to x sine y. As a special case, when z is pure imaginary variable, like if z equal to ix, therefore we will get sine x equal to e to ix minus e to minus ix over 2I, and cosine x will be equal to e to ix plus e to minus ix over just 2. As a generalization, sine z will be equal to e to iz minus e to minus iz over 2I, and cosine z equal to e to iz plus e to minus iz over 2. From this one here, tan z is actually equal to sine z over cosine z. Now let's define hyperbolic functions. Sine hyperbolic z equal to e to z minus e to minus z over 2, and cosine hyperbolic z equal to e to z plus e to minus z over 2. And from these two definitions, we can find the rest of the hyperbolic functions. Example: calculate sine ix cosine ix and tan ix in such a way x is a real variable. Here x is a real variable. Now sine ix equal to, use the definition, e to I ix, instead of x use ix, minus e to minus I x over 2I, which is equal to e to minus x minus e to x over 2I, which is equal to e to x minus e to minus x over 2, all multiplied by I, or in other words, it's equal to I sine hyperbolic x. Therefore, sine ix will be equal to I sine hyperbolic x. By following the same procedure, let's find cosine ix. So cosine ix, use the definition, and instead of x use ix, e to ix plus e to minus ix divided by 2, which equal to e to minus x plus e to x over 2, and therefore cosine ix is equal to cosine hyperbolic x. Now let's define tan ix will be equal to, remember tan it's sine over cosine, so it's sine ix divided by cosine ix, and this will be equal to I, remember sine ix equal to I sine hyperbolic x divided by cosine ix is equal to, we just calculated this one here, it's cosine hyperbolic x, and therefore tan ix it's equal to I tan hyperbolic x. Example, calculate sine hyperbolic ix cosine hyperbolic ix and tan hyperbolic ix. Now let's start with sine hyperbolic ix equal to e to ix minus e to minus ix over 2, and this is actually the definition of I sine x, and cosine hyperbolic ix equal to e to ix plus e to minus ix over 2, and this is the definition of cosine x. Tan hyperbolic ix equal to sine hyperbolic ix over cosine hyperbolic ix, which is actually I tan x. Now let's define the logarithmic function. If z1 equal to e to the power omega 1 and z2 equal to e to the power omega 2, therefore z1 z2 equal to e to omega 1 e to omega 2, which is equal to e to omega 1 plus omega 2. So the logarithmic function, let's define this one here. If we take ln for both sides of this one here, so ln z1 Z2 will be equal to omega 1 plus omega 2, which actually equal to, now omega 1 from this one here, it's len Z1, and omega 2 from this one here, it's len Z2. Therefore, if Z equal to R e to I theta plus 2m pi, this one, then omega equal to len Z, which is equal to len R e to I theta plus 2m pi, or len R plus I theta plus 2m pi, and m in this case it's equal to 0 plus minus 1 plus minus 2 and so on. Example, find len minus 1. So in this case here, let's put minus 1 into polar form. So minus 1 equal to e to I pi plus 2m pi, and m here equal to, we just define it 0 plus minus 1 and so on. Remember, r in this case it's equal to 1, and theta it's equal to pi. Then len minus 1 equal to len, just use this one here, this definition, len 1 plus I theta, it's pi plus 2m pi, and len 1 is 0, so len minus 1 equal to I pi plus 2m pi, and that's it. Example, find len 1 plus I, and again let's put 1 plus I in polar form. R in this case it's equal to square root of 2, theta it's equal to pi over 4. So 1 plus I equal to square root of 2 e to I pi over 4 plus 2m pi. Therefore, len 1 plus I equal to len square root of 2 plus I pi over 4 plus 2m pi. Use the calculator, you can find len square root of 2, which is 0.347 plus I pi over 4 plus 2m pi, and remember m equal to 0 plus minus 1 and plus minus 2. Let's define complex powers and roots. If we have len x to the power y, this actually equal to y len x, and therefore if we take the exponential for both sides here, so x to the power y equal to e to y len x, or in other words, x to the power y equal to e to len x all to the power y. Example, find I to the power minus I. To solve this one here, now I to the power minus I equal to e to I ln I, and I in this case equal to e to I by over 2 plus 2m pi, because r in this case it's equal to 1 and theta equal to y, which is 1 over x equal to 0, so it's pi over 2. Therefore, I to the power minus I equal to e2 minus I ln 1 plus I pi over 2 plus 2m pi. We just use this definition here for the logarithmic one, this definition right here. And this equal to e2 ln 1 equal to 0, and minus I times I is just 1, e2 pi over 2 plus 2m pi, and remember m in this case equal to 0 plus minus 1 and so on. Therefore, I to the power minus I has an infinite number of real values. Has example, find 1 minus I to the power I. Therefore, 1 minus I to the power I equal to e to I ln 1 minus I, and remember 1 minus I, r equal to square root of 2, square root of 2 e2, and theta minus pi over 4 plus 2m pi. Therefore, 1 minus I to the power I equal to e to I ln square root of 2 plus I minus pi over 4 plus 2m pi, or it's equal to e to I 0.347 ln square root of 2 minus pi over 4 plus 2m pi, e to pi over 4 minus 2m pi cosine 347 plus I sine 0.347, and upon simplifying this one here, it's equal to e to pi over 4 minus 2m pi times 0.94 plus I 0.34. Therefore, 1 minus I to the power I, again it has an infinite number of complex values. One very serious note is that you have to be more careful when dealing with the product of two complex powers like z z to the power omega 1, z to the power omega 2, because z to the power 1 times z to the power omega 2 equal to e to omega 1 ln z1 times e to omega 2 ln z2. But ln z equal to ln r plus I theta plus 2m pi. Therefore, z to the power omega 1 times z to the power omega 2 will be equal to e to omega 1 omega 2 ln r times e to I theta omega 1 plus omega 2 times e to 2i m omega 1 plus m prime omega 2 pi. In such a way, m equal to 0 plus minus 1 plus minus 2 and so on, which means that z to the power omega 1 times z to the power omega 2 is not equal to z to the power omega 1 plus omega 2, because z to the power omega 1 plus omega 2 equal to e to omega 1 plus omega 2 ln z. That's it. Thank you for watching.